All right, 9 minutes has passed. It looks like most of you have submitted that. So let's have everybody come back. And go ahead and unmute yourselves for me too, please. Pretty cool, huh? It's amazing how many people were involved in making that video. So, Barrett, can you hold up that little diagram you drew again that you showed me? It might still be working.
Yeah, for sure.
Barrett's actually got a little diagram. So what was the airplane doing?
It's just going up and down, just like so it can it goes zero gravity at the top, and then you get like double going up and then double going down.
Yep. And so they call it a parabola, but in reality, it's really simple. So if you've got an object on your desk, pick up something that you can toss into the air. I don't care what it is, ball, pillow, whatever you've got like that. Think about when you throw something upwards, right? Like that. Throw it a few times. What you're doing essentially is that when you throw that object, you're applying about 2 G's worth, right, to it as you throw it in the air, because right now it's experiencing 1 G, and then you're applying about another G to launch it up into the air. But you'll notice as it kind of gets up in the air, it floats for a second, right? It's sort of got that's that zero gravity experience is when it slows down, comes still, and falls back. But then when you catch it again, it experiences that same 2 G's as it comes to a halt again in your hand. That's what the airplane was doing to them. It was literally taking their bodies, throwing their bodies into the air. They were then falling with the airplane and coming back down, which is kind of cool. And really weird to think about that. So does anyone know what affectionate term they call these airplane rides?
Bullet planes.
Yeah, they call them the vomit comet is a common name, right? Because again, we'll take a look at some of these questions here. So we kind of went through these first 3 already, but the reason they experience double gravity, most of you got it, is that they are literally accelerating upwards in the airplane, right? Think of the airplane as like throwing them up, like just like you throw a pen in the air. They experience zero gravity because they are then falling with the airplane. So think about what the pilot has to do, right? The pilot essentially powers down the engine, and you just have to let the airplane sort of glide in an arc and then start to fall. It's just got to be kind of a creepy experience as a pilot, but they know what they're doing. And then the airplane catches them again as the pilot then re-engages the engines and they start to accelerate again, and gravity also comes back at the same time. And so pretty cool to think, and not very much time that you have in order to do that. So did you guys notice the little waiting periods where gravity came back?
Yeah, like you could like see like the balls like going to the floor.
Yeah, once they have a lot of clutter around them, you can definitely see the moments where it all falls down. But you also notice that between the dance routines, they always went back to their seats. And that was sort of another moment where gravity definitely returned. So what are the 2 common ways that people respond to weightlessness?
Flail and swim? Or just
swimming and vomiting. And so that's why they call it the vomit comet. Apparently these things smell really bad. And it's funny that because you're swimming, you think you are falling. But one point I should emphasize too with all of this is that were they actually experiencing zero gravity in that?
No.
They weren't. They were actually experiencing just as much gravity as all of us do, right? It was just that they had no apparent weight. And that's because as the airplane was falling, they were falling inside of it, and they're able to move around like they would if they were actually weightless. Right? They couldn't, if they stood on a bathroom scale during those falling periods, they would register no weight. And so I know we say zero gravity, but in reality, it's actually that they're just, their apparent weight is nothing, right? That they're apparently weightless. So be honest, how many of you would sign up to fly in a plane like this? Would you want to experience zero gravity? Yeah? All right, brave people. I don't think my stomach can handle it. And so that's going to bring us to our next activity is how do we perceive gravity? Right? How do you think, what part of your biology tells you which way is down, right? How do we know our body position? Anyone know? Is it just your brain?
We have like something in our brains,
Is
like
it your spine?
Yeah, it's our sense of like brain, our sense of direction.
Yeah, it's part of your brain.
It's very close to your brain, but it's actually an inner structure in your ear. So in both of your ears, you have these weird circular structures. It's on the inside. And that they're full of liquid and all these little tiny hairs. And the liquid is moving with gravity, right? When you lay down, the liquid moves one way. When you stand up, the liquid moves another way. the hairs respond to it, and that's what gives you your sense of balance. And it's also our vision, right? We use our eyes a lot to figure out what's level, right? You know when you're upside down if you're seeing upside down, right? But does anyone
like? I remember one time I was in the ocean and I got caught in a wave and I was underneath the water and I didn't know, but I was like stuck and I didn't know which way was up and down and I ended up swimming down.
Yeah, especially if you get spun around a lot in a wave. Yeah, then you get really
so that
disoriented.
happens. Like that's.
Yeah, you can lose your sense again if the liquids inside your ear suddenly got confused. Then yeah, you could lose all perception of which way is up or down. A lot of people who have really bad ear infections sometimes start to get really dizzy and can't walk because the swelling of the ear infection starts to press on your balance mechanism. And it's really cool. They've actually taken the biology of our ear structure, and that's what they've put into phones. You guys ever noticed your iPhone, when you tilt the screen sideways, the screen corrects itself? That was a feature that they have there's a little tiny magnetic mechanism in there that works in a very similar way. And it can break sometimes, but it's kind of cool that it's based off of the biology. So, but does anyone know, how do you feel if the gravity registration you're getting from your ears does not correspond with what your eyes are seeing? How does that make you feel sometimes if like your eyes are telling you you're moving, but your ears telling you you aren't, or vice versa?
Dizzy.
Yeah, you get dizzy and you get nauseous. Anyone ever been seasick before? Right? So seasickness is a result of that because your ears are like, whoa, we're moving everywhere, but your eyes are like, no, the horizon's level. And so your brain is like, I don't know what's going on and I don't feel good about it. Car sickness works the same way, especially if you try to like read in a car because you're looking at a book and you're reading, but your ears are like, no, we're moving. And so there's all kinds of weird things that happen. And so that's one thing that was making them sick too. But yeah, your sense of balance it all comes down to your ears. So I want to do a little activity today where we are going to explore your sense of balance. Again, it's going to involve a Flipgrid video post. So I'll actually play this video for you all. It should work all right, but I made a little demonstration video. So we'll watch this and then I'll let you loose to work on it. Is everyone seeing the image of me?
Mm-hmm.
Yeah.
All right, my Wilson apartment. Oops. Hi, Science 2 kiddos. I'm going to do a couple of balancing activities today. How's the audio?
That's pretty good.
We're good? Okay. The organ that gives you a sense of balance is actually your ears. And we're going to learn some of the details about that, but that is how we perceive gravity and get an idea of which way is down, which is something we've been working on. But your vision and eyesight also plays an important role, as you'll see. So to play around with your sense of balance, we're going to be using our feet, standing on one leg and using your feet to move objects from one container into another. So you'll need something that you can either pick up with your toes by grabbing it, or that you can scoop your foot under it and lift and move. You could use bean bags if you have bean bags at home. I kind of made my own bean bags, just took Ziploc bags. This one's full of Cheerios, so you can use cereals if you want. Don't be wasteful. Like I'll put these back in so that we can eat them. If you've got like some kind of little toy that's in multiple pieces, these are like little magnetic letters from the fridge. You could even like use candy. This is a bag full of Butterfingers. Hopefully I won't be a Butterfinger and drop it. Get it? Or if you're really up for a challenge, you could use something heavier, like this is a bag of cuties, or maybe even like a bag of potatoes or something. That would be a pretty big challenge for balance. However, you only need 3 of them, right? So I'll get rid of it. All right, so what you're going to do is transfer these 3 items from one container into another. So you need something. You can see I have a basket and just a pot here at home, but whatever large container you have, just get 2 of them. Make sure the bags can fit inside of them. Want to make sure you're in an open space and somewhere safe where you're not going to fall and like hit your head on anything dangerous, and you want to be able to like spread your arms out because that's going to be an important part of balancing. We're going to do this in 4 different ways, and always use the leg that corresponds with the motion. So if you're moving the items from the right to the left, use your right leg, right to left, right to left. If you're moving the items from left to right, use your left leg, go this way. You'll see that by crossing over, it actually makes the balancing a little harder. You're welcome to try that if you want, but I'll just keep these simple. So the first round, you just want to have your eyes open and your arms out for balance. And again, just transfer the 3 items. like so. These are a little more challenging for me. All right. The next round is the same thing. You can have your arms out, but now you've got to have your eyes closed. So, and notice again, I'm using my other foot now because I'm going from left to right. So just get an idea of where your containers are, but then close your eyes and see if you can move the items over. See, it's a little more challenging. Oops. Okay. All right, third round, you want to have your eyes open again, but this time your arms are held behind your back. Again, I'm using my right foot to go from right to left. Cuties are definitely harder. Okay, for the final round, you want to combine both things. You want to have your arms behind your back and your eyes closed. This should be the most challenging one. So again, get your bearings. Here we go. Again, you'll see that having your vision makes things a little harder. Okay. All right. So your challenge is to do those 4 activities as quickly as you can and film it and upload it with Flipgrid. So you might want to get a parent or guardian or a sibling to either help film you or position your camera in such a way that you can film your feet and the ground and what you're doing with your feet. And you can just use the video as your timer, right? So start the video, get set, and then we'll just see who can do it, those 4 activities in the fastest amount of time with the fewest stumbles. So you don't want to rush because if you're stumbling around everywhere, then that's not technically going to count, right? We want to see who can be the most stable and do it the fastest. So that's your challenge. As always, be safe, right? Make sure there's nothing dangerous around you that you're going to fall on. And always clean up after yourself, so make sure you put your items away and emptied your bags once you're done. All right, and so the Flipgrid is already assigned right here. It's called the Balance Challenge, and that's where you'll post those things. All right, kiddos, any questions on that?
When is this due?
Well, I'll give you about 20 minutes to work on it right now, but it'll roll into homework. So if you don't get it done, it's okay. You can at least maybe try to get the materials and get set up. But I'll let us go for about 20 minutes, I think, to work on this. So maybe, I don't know. I mean, I don't even know if it'll take 15. Let's try for 15 minutes and just see how far we get. You can report back to me about whether or not you get it done. All right, kids, listen. Swimming pools, staircases, glass doors, you need to stay away from, okay? I don't want to end up on America's Funniest Home Videos or any of that stuff. So you guys think you'll be able to get the materials that you need? Cool. All right, so let's go for, I don't know, I mean, it's 38 right now. I would like at least another 10 minutes. Let's see, minute 3:05:55. Yeah, I mean, if we go for 15 minutes, then let's be back here at 2:55. So 2:55, return to the room, and we'll check in then. But again, if you don't have a video done, it's okay. It'll roll into homework. So go for it. All right, it is 2:55. Let's all come back in. How was that, everybody?
It was challenging.
So I managed to watch 3 videos. So yeah, it looked like you were doing pretty good. Win was very focused. Win, I really like the mirror you've got behind you though, so we get the front and back view. So
Nice.
pretty good. So.
I even noticed that. Yeah, I picked really small items, and with socks, it was
I
like
was about to
really
say, having
hard
your
to like
socks on, that's like an added
grip
challenge.
it. Yeah, no, it wasn't the play.
Yeah. Well, you're welcome to reshoot if you want with bare feet. So for those of you who tried it, did it get harder with your eyes closed?
Yes, like so much harder. I almost fell over. I was like, oh, oh, oh. I was like going everywhere.
Yeah.
And then when I had to put my hands behind my back, I like started jumping like crazy because I was like, just didn't know where I was.
Yep. Yeah. So again, that's what balance is all about. I mean, it's all rigged up your nervous system, but yeah, we use our arms for balance a lot. When you remove that factor, it gets a lot harder. And then, yeah, not having your vision to sort of give you like a sense of level and where things are. Not only, I mean, for me, honestly, what struck me was with my eyes closed, it wasn't even that hard reaching into the bowl to like actually extract things out, like actually finding what I wanted. It was just more, again, it was that balance. So anyone else have what was the hardest part, would you say?
Honestly, for me, like I have a broken toe from when I was like younger, so it's like my big toe. So whenever I use like my right foot to try to grab stuff, it was like really hard. So I was like going
Yeah.
everywhere.
Yeah. Niles, did you give it a try?
Yes, I did. It was
Yeah.
really hard picking up the items.
Yep.
It started with my socks, and so I had to take my socks off, and it was still even harder for me.
Yep. Yeah, well, and it's interesting too, being you said you're a basketball player, and I know a lot of other athletes too. Even when doing things like track and running, you work on balance stuff, like when you're stretching and doing that, and so you kind of become aware of that. Especially if you're doing like dynamic stretches where you're bending over, you start to wobble a little bit because again, you've changed orientation, your eyesight, you're looking down instead of level. So it gets tricky. But anyway, this was just meant to be a silly activity to explore that a bit. So. We got a few minutes left. What I want to do is start us off on another little instructional video exploring some of the math behind calculating gravitational force and how we experience gravity. So bear with me. We'll do this right up until 3:05, and then I'll let you guys go. I just want to get you started, and it's basically going to lead into an opportunity for extra credit. So if you want to take a few notes or write a few things down based on this video, you're welcome to do so. But again, I'll just start playing it. It's still available. You can watch it later too if you want. But this is going to be all about using that equation that relates mass and force. And this is me using notability, which I know some math classes have used. So let me pull this up and should play.
Hi, Science 2 kiddos. I'm going to show you some of the math behind calculating gravitational force. This relates to chapter 5.5 in the Hewitt textbook.
Everyone seeing the image and hearing the audio okay? All right.
But before we talk about that, we have to talk about calculating what's called a gravitational constant, which is a number that sort of puts gravity in context and brings newtons into the math. So we'll define it really quickly. I'll use that same gravity force FET simulation you did for homework to then do some of the math. And if you feel up to it, as an optional extra credit challenge, you can try doing one of these math problems on your own. Again, this is sort of more at the honors level in terms of the math, but you're welcome to give it a try if you want, but I won't require you to do it. So chapter 5.5 in Hewitt defines the universal constant of gravitation as a very small number that represents the very weak force of gravity, right? We often think gravity is being very powerful, but it's actually technically a weak force. It also brings newtons into the equation, which is the unit used to measure force. And again, it relates it to the mass and distance equation that we saw from Newton earlier, right? We've talked about this before, you've read about this. Here's your gravitational force. We can see that it is directly proportional to mass, right? The larger the mass is, the more gravitational force, right? Earth exerts a lot of force on us because Earth is very massive, but it's inversely proportional to distance, right? The further away you get from an object, the less gravitational force you can feel from it. The farther away you get from Earth, the less gravitational force you feel from Earth. They define the gravitational constant as being equal to the force between two 1 kilogram masses 1 meter apart. So imagine you had 1 kilogram mass and a 1 kilogram mass exactly 1 meter apart, sort of like in that simulation, but these are on a much smaller scale. What this means is that the gravitational force that these two masses would be exerting on each other would be equal to that very small number right there. And so we can rewrite that in scientific notation form as 6.67 times 10 to the negative 11. Again, that negative 11 there tells you it's a very, very small number. Gravity is a very weak force. It also has a crazy unit on it, newtons meters.
Oops. Oh, don't fail me now, internet. Sorry, kiddos. Let me just reload the page here. Sitting for too long.
Hi, Science 2. It's 10 to the negative 11. Again, that negative 11 there tells you it's a very, very small number. Gravity is a very weak force. It also has a crazy unit on it, newtons meters squared per kilogram squared, but you'll see in the math where that comes from. So I took a screenshot of the PhET simulation in its standard setting, and I want to see now is this accurate? Can we actually calculate the value for the gravitational constant g using these numbers? If it is accurate, the answer I should get is right there, 6.67 times 10 to the negative 11. And so we'll see if that's the number that I actually get from my math.
So just looking at this really quickly, so here's the image from that PhET simulation you did for homework, and we'll pick up with this in our next lesson. But looking at the equation, F equals G M1 M2 over D2, I'm trying to find G. Can anyone tell me what F is? What number are we going to put for F?
6. I don't know.
30.
Like what it symbolizes or the number?
Yeah. What do you think F stands for?
It's the force of Newton.
Force. So yeah, what would the force be here?
33.4.
Yeah, there you go. See 33.4. Now, I know some of you are like, wait, but there's two forces, right? There's force going this way, force going that way. What do you notice about the two numbers?
They're equal.
They're equal.
Right. So yeah, so we use that as our force, 33.4. Okay, what do you think M1 is?
Mass.
The
The
first
mass of the first one though.
And that would be 2 billion kilograms, right? What about M2?
second
Mass
object
is second
now.
one.
Yep, 4 billion kilograms. And then what's D?
Distance.
Distance.
Yep, 4 kilometers right there. But you'll see it has to be in meters. So again, I'll play through this a little bit and explain it.
Plug in the numbers. The force, F, is right here, 33.4 newtons. And again, I know force seems to be given twice, but notice that it's always the same number, right? The force is always equal, so that's what we'll use there in newtons. Mass 1, you can see right here, is 2 billion kilograms. I'm going to rewrite that as 2 times 10 to the 9th kilograms. That's billion right there. Mass 2 is right here. It's going to be 4 billion kilograms. That would be 4 times 10 to the 9th. And the distance between them is going to be 4 kilometers. But you'll notice in the gravitational constant, the distance is actually in meters. So we can't use kilometers. We have to convert that into 4,000 meters. That's how many meters are in 4 kilometers. So if I plug those numbers into the equation right here, again, this is using the same equation, just plugged in all those numbers. It looks kind of complicated. So I want to get G by itself. I want to simplify.
All right, I'm going to stop it there. I go on to then kind of walk through the math with 2 different examples. The very last slide. So here's the slideshow, which you also have available, the link. The very last slide is a sort of an extra credit challenge. So I encourage you to watch the rest of that video. If you feel up to it, and you've got a calculator available, try solving a problem on your own. Again, this is optional, is not required. But if you can, show me your work. Either take a picture of your notebook, or if you do it online somehow, just send me an image. But you got to show your work, because you could just open up the simulation and make these settings, and then you could get the correct answer. You'll see I've covered it over here. Or sorry, am I sharing my screen? Here we go. So this is the last slide in that slideshow, which is available to you. And so use this equation to solve for F. But again, that's just part of optional work. The actual homework is on the very bottom here. I would like you to read Hewitt 5.5 through 5.6, which is going to go into balancing and how your ear senses balance, and also the value for G. So we'll continue to review this. Take notes for a short reading quiz. I would like you to answer questions 8, 10, 12, and 14 in those reading check questions on page 116. That's the only required homework. Everything else is optional. I also have a much longer video here about the OK Go video. If you enjoyed that, that's about a 20-minute little documentary on how they made it. And it's pretty entertaining in my opinion. So, all right, any other questions about that? All right, well, thanks to our guest, Niall. It was a pleasure having you. I hope this was somewhat interesting. Thank you very much, kids. Have a good day. That's all for me.
Thank you.
But
Thank you. Bye. Thank you.
Thank you.